Hello everyone, and welcome to our first video on functions and their inverses. So the goal of this two-part series is just to get a good, strong understanding of what an inverse is, and therefore what an inverse function is, and that'll make it a lot easier to understand logarithmic functions when we get to that. So, before we talk about inverse functions, we need to know what inverse means in general, mathematically speaking, and that's going to require a little bit of a detour. So, definition. We're going to need a few definitions here, but we'll get through them. A set is a collection of distinct, in other words, unique objects. The objects in a set are called elements. So a set just means here's a bunch of things that are all unique. There's one of each of them, is what we're saying. So, for example, this set A here has a cat, a dog, and a parrot in it. And this set B here is the collection of numbers 2, 3, 5, 7, and 11, which you might notice is all of the prime numbers between 2 and 11. So set A has 3 elements, set B has 5 elements. So the key thing is the uniqueness. We never list an element twice in a set. A set only has each object one time. All right, so definition. A function is a rule that assigns each input of a set D, called the domain, to a unique output of a set R, called the range. So we'll look at 2 examples. First, you should consider a soda machine. Right? So all a function says is for each input there is just one output. So like a soda machine, if you hit a button, you should know what you're going to get. Right? Like if you go to a soda machine and you press for, let's call it soda A, and out pops soda B, that's going to be a problem, right? You didn't get the soda you wanted. So the point of functions is predictability. They're rules that always give you the same output for a given input. And anything that fits that criteria is a function. So now let's look at some little diagrams of potential functions. So in this first diagram, we've got a domain with these 3 elements, x, y, and z. And the function sends x to 1, y to 3, and z to 2. That's a function, right? Each one of these goes to exactly one output. On the other hand, this function here, its inputs are a, b, and c. And this one, a, gets sent to cat, b gets sent to dog, and c gets sent to dog. This is still a function. Each input has only one output. Yes, B and C both go to the same output, but that's fine. Many soda machines have 2 buttons for the same soda. That's perfectly fine as long as you know what you're getting on that output. Now let's consider this third diagram. In this case, 1 goes to A, but 1 also goes to B, and right there we can stop. This is not a function. If you had a soda machine where you pressed a button and you didn't know which soda you were going to get, it just popped out something random every time, you'd probably be pretty unhappy. Right? Unless, I suppose they could do a promotional thing with that, but it wouldn't be a function. Right? And that's the whole point, is that a function has predictability. Each input has only one output. This is not a function. Okay. Now, I'm going to loosely define this. We use the term operation to refer to functions in particular contexts. So, like addition, subtraction, multiplication, division. These operations have input pairs with unique outputs. So if you add 3 plus 4, you always get 7. It doesn't change, right? So that addition is a function. It's a function on 2 inputs. It takes 2 inputs to a single output. And there's, many different types of operations, but we specifically use this word in different contexts in mathematics, but it's a more It's reserved for specific things, usually like addition, subtraction, multiplication, division, and another operation that we'll talk about in a little bit. All right. Now here we're going to get to a heavy definition. So this is a pretty big one and not something that would often be covered in the context of pre-calculus, but I truly believe that understanding this concept at a basic level really will make inverse functions much easier to understand. So what we're going to talk about is a mathematical object called a group. It's a set G, so that's a collection of objects, paired with an operation, star. We don't know what operation it is, we'll just call it star, which takes two elements in G, A and B, and assigns them to a new element, A star B. And a group must satisfy four properties. So the first property is that it has an identity. There must be a unique element, I, in G, such that I star A equals A, and A star I equals A, for all elements A in G. So if you take a look down here at this example 3, addition. So in this case, this operation we're talking about, we could be talking about addition. And addition has an identity. Its identity is 0. So if I do 0 plus 3, I get 3. I star A, I get A. If I do 3 plus 0, I get 3. A star I equals A. And this is true no matter what number you add 0 to. 5 plus 0 is 5, etc. Right? 0 is the identity for addition. Right? Okay, inverse. For each A in G, there is an A to the negative first power. What we really say this is A inverse, right? In G, such that A star A inverse is equal to I, and A inverse star A is also equal to I. Right? This is called the inverse of A. So each element has an inverse. So when we're talking about addition on integers, what would the inverses be? Well, okay, if I take 4 and I add a negative 4, I get 0. Right? So that's A star A inverse equals I. 4 plus negative 4 equals 0. And if I take negative 4 and then add 4 to that, I get 0. Same thing. A inverse star A equals I. So when I take and I add a number and it's negative, I always get the identity, which is 0. So we say that negatives are the inverses for addition. All right, and third property is associativity. Means if I do my operation A star B first and then operate it with C, I get the same thing if I first operated B star C and then did A star that result. And we know that addition is associative. We can group in any order for addition, so that's fine. And finally, the closure property. If A and B are both in G, then A star B is in G. So for addition on integers, if I add two integers together, I always get an integer, right? 6 plus 2 is 8. 8's still an integer. Now similarly, addition on integers is not the only group you know. Multiplication with the rational numbers also forms a group, but we have to exclude 0, which I'll talk about in a moment. So, well, let's look at why is this a group? Well, it has an identity. The identity is 1. Right? If I take, say, 2/3 times 1, I get 2/3. If I take 1 times 2/3, I get 2/3, right? So when it comes to multiplication, 1 is the identity. Now, what about inverses, right? To be a group, it's got to have this inverse, something where when I operate it, I get the identity. So I need something that when I operate it, I get 1. Well, if I had started with, say, 5, then 1/5 would be the inverse, the multiplicative inverse, because 5 times 1/5 is 1. Similarly, 1/5 times 5 is 1. Right? That's a multiplicative inverse. Okay, and multiplication is also associative. I can group in any order I want when I'm multiplying things, right? I get the same thing, 1/3 times 2/4 first times 3/5. It's the same thing as if I did 2/4 times 3/5 and then multiplied the 1/3 in front. And finally, if I multiply two rational numbers, I still get a rational number. It's still a fraction with an integer on top and bottom, so it's still a rational number, so it satisfies the closure property. All right, so both of these things, addition with integers and multiplication with rational numbers, are groups. But with multiplication, we had to exclude 0. And the reason is because 0 couldn't have an inverse. There's no number that you can multiply 0 by to get 1. So we have to cut it out if we want to form a group and use group properties. Okay, well, we've got some idea of what a group is now, hopefully. All right, now let's notice the following. Using inverses is how we solve algebraic equations. So you might not have ever thought of it this way before, but that's actually what you're doing. Let's take a look at A here. If I have 5 plus x equals 7, if I want to solve this, I want to isolate x. In other words, I want to undo the operation of adding 5 to it. So what we do when we solve this algebraically is we add its inverse. Then we do the same thing to both sides so as to keep the equation balanced. And when I add -5 plus 5, I get 0, which gives me x equals -5 plus 7, which is 2. Right? So what did we do here? We added a negative, which is, in other words, an additive inverse. And if we look at this example B here, it's the same kind of idea. See, solving these addition equations or these multiplication equations, they're actually the same technique, even if it doesn't look like it. Right? So if I think of 2/3, well, what did we say? We said reciprocals are the inverses for multiplications. If I want to get rid of the 2/3, if I want to turn it into a 1, I multiply by the reciprocal 3/2. So that cancels and I get x equals 12/2, which is 6. Right? So in both of these cases, all we're doing is operating inverses. And that's the motivation for considering inverse functions. When we have more complicated functions and we want to be able to manipulate them to solve equations or analyze their properties, we might like to use their inverses in order to do that. So we need a more rigorous understanding of inverses to be able to do that confidently. Okay, so now we can consider the question of inverse functions in the next part of this video series. So I hope this was helpful so far, and I hope it was informative. Thank you for watching, and I hope you'll enjoy part 2 next.